Um, we're joined today by Joe Johnson, who is the Byrne and Sulin Endowed Professor in the Department of Electrical and Computer Engineering and Electroscience Laboratory of the Ohio State University. Joe's research is in the area of microwave remote sensing, propagation, and electromagnetic wave theory. He's an IEEE fellow and an active participant in the IEEE Geosciences and Remote Sensing Society and the International Union of Radio Science. We're really excited to learn about how the spectrum is used for remote sensing, climate, and weather prediction. And so, Joel, thanks for joining us once again, and please take it away.
Okay. Thanks, Maria. Nice to talk to everybody here. I'll go back to sharing the screen here. Let's see here, get this in full screen mode. So I'm assuming everybody can see my screen now, all right?
Yep, it's coming through great.
Yes. Okay, great. All right. Yes, I'm Joel Johnson from Ohio State. Going to talk to you about another non-commercial use of the spectrum, which is sensing the Earth's properties, in particular using microwave radiometry to sense properties of the Earth. And I want to acknowledge some contributions to this talk from my collaborator, Mustafa Axel of University of Albany. So, so microwave radiometry, here we're talking about it in terms of observing natural properties of the Earth. And if you haven't heard of this kind of technology before, what we're observing in this are naturally emitted noise signals coming from the environment. So you may not have thought about that before, but we're observing the naturally emitted microwaves coming from the environment, and those, it turns out, by measuring that, you can get very valuable measurements of the environment, such as properties of the atmosphere, like water vapor, like the temperature versus altitude, properties of the surface, like the temperature of the sea surface, winds over the ocean, soil moisture in the land surface, salinity of the ocean, various properties of the cryosphere. A lot of very useful information you can get from these kind of measurements. And we want to do this in the microwave band because you can see through clouds. You have sensitivity to some products that other sensors can't give you. For example, optical measurements. There are some things you can only measure with microwaves. So because of this, there's been a long history of deployment of satellites in space, microwave radiometers in space, measuring these kind of properties, and they've been very valuable for our understanding of Earth systems, Earth's climate, weather. In some cases, these are some of the most impactful measurements we have for improving weather forecasts, for studying the Earth's ocean, studying Earth's land surface, and so on. So these are important measurements, very useful. I think everybody agrees it's important to monitor the state of our planet, no matter what your background might be. So I'm going to be talking to you today some about kind of how it works and what the instruments are like to do this and why they need spectrum access. Here's a plot down here of the frequency spectrum, okay, between 6 and 40 gigahertz. All right. So the plot down in the bottom part is showing you these sort of curves here indicate the sensitivity in different frequencies to different environmental properties. For example, the black curve is vegetation, the blue one is soil moisture, the green one is sea surface temperature, and so on. And you can also see down here, these little bars indicate where there are allocations that exist for doing microwave radiometry, with the green bars being primary allocations, the yellow bars being secondary allocations. Um, Primary allocations in this case, similar to radio astronomy, meaning that because we're trying to do noise sensing, no one else should be transmitting there, or any emission should be at a very extremely low level from anybody else, sort of quiet bands. Secondary allocation means that there are other users, but things are sort of designed where microwave radiometry should still be possible. And then the red is where there's no allocation. And then in addition, these are lists of radiometers in space. And what we see here are the frequency channels that those particular radiometers were using. And you can see there's a variety of different frequency bands used, but there's sort of some commonalities here because there are particular utilities of particular frequencies we'll talk about a little bit. You can see these correspond to different peaks of sensitivity down here. And a lot of radiometers observe on multiple bands simultaneously because they're trying to separate out different geophysical products by combining the measurements at different frequency channels, and be saying more about that as we go through this talk today. So again, the goal is just to introduce you to this idea of microwave radiometry. How does it work? What are the instruments like? Why do we need spectrum access? Um, so it's a little bit different. This talk's a little bit different than other talks about communication systems. Because, in a communication system, you have a signal you're trying to measure. You're trying to communicate from one place, from transmitter to receiver, and your receiver receives some noise in addition to the transmitted signal. Okay, so if we call the signal we want to receive has power P sub S, then we usually think of it, if you're a signal processing person, as you get signal plus noise, and noise is some, usually we model as additive white Gaussian noise. And a lot of times we don't worry about that too much. We describe it as some Gaussian signal. It's got a variance that some, corresponds to some number of watts. The variance might be written like sigma n squared over 2. But really, when you look at your comm system performance, it's all about signal power to noise power, signal to noise power. And our bit rate or throughput or whatever will be described in terms of the signal to noise ratio. So we don't really care about what the absolute value of the noise power is, as long as it's, some low compared to the signal power, we're happy, and we just care about this ratio. But in radiometry, and also in radio astronomy, I think the problem is basically reversed. What we're trying to measure is that noise power. That's what we care about. We don't want there to be any signal power. We just want to measure the noise. And in fact, we want to measure the noise to a very high degree of precision. And I think this is in common between Earth observing radiometry and radio astronomy. Both of us, we want to have a precise measurement of what that noise power is. Okay, so in radiometry, again, we're trying to measure this natural noise power. Now, in a receiver, you have noise generated by the receiver itself, and then the receiver picks up external noise. And it's the external noise we care about. So we measure both the internal and external noise together. Sometimes the external noise is a small fraction of the internal. So again, we need to measure it very precisely to be able to measure the external noise precisely. And as you do that, again, we're talking about noise here, random signals. They have a Gaussian distribution. And if we're trying, each measurement that we take is a sample of that Gaussian distribution. We're trying to estimate the mean power. So if you want to estimate the mean of a random quantity very precisely, what do? You take a lot of samples and average them. So if we want to have the very precise measurement of that noise power, we're going to take a lot of measurements and average them. And as we average them, the variance of the estimate of the average decreases. And it decreases, the standard deviation of the estimator decreases 1 over the square root of n, where n is the number of samples averaged. This is what you learn when you study the central limit theorem, for example, or basic probability class. In Earth observing radiometry, that translates into the precision that we get in measuring this noise power goes as 1 over the square root of the time bandwidth product of our measurement that we make. So in radiometers, the time bandwidth product of your measurement is a very key parameter. So here, B means bandwidth, how wide is the frequency band you're measuring over? And tau means integration time. How long did you have to take this measurement? The product of those two is a unitless quantity, and the precision you get in doing your brightness temperature measurement goes as 1 over the square root of that quantity. So if we have a bigger bandwidth, we can get more precision. It's kind of an interesting contrast with a communication system. Um, in a communication system, bigger bandwidth means higher data rate. We want higher data rate, we need bigger bandwidth, and that's pushing the drive for, communication systems needing more and more allocation. In radiometry, we're not getting a data rate from our bandwidth. We're taking our bandwidth and we're just averaging. You could have had a lot of data rate in there, but we're averaging that like crazy and translating that high data rate we could have had into a very high precision in measuring the noise power. So we're exchanging this potential data rate for very high precision in making our measurement of this thermal noise power. And basically by making more precise measurements of the thermal noise power, you get more precise measurements of atmospheric water vapor or sea surface salinity and so on and so forth. So precision in measuring this noise power translates to precision in our ability to observe the environment. So in terms of spectrum access, that's probably one of the main driving factors here is that more bandwidth translates to more precision. And also feel free to interrupt me with questions at any time. I'm happy to explain things more if there's any questions. Now, in when we make a radiometer, we're measuring noise power. Okay, so in terms of communication system, we'd be thinking of this. This is the power of the thermal noise that is corrupting our communication signal. But in the world of radiometry, also radio astronomy, I think there's a relationship we can form between the power we observe, the number of watts we observe, and an equivalent temperature that this noise power corresponds to. Okay, so it turns out in reality in this field, we talk about noise powers in terms of temperatures measured in kelvins a lot instead of in terms of watts. And the basic relationship about that is this formula here that, if you have a noise source, an ideal noise source that emits power, absorbs and emits power perfectly, then the noise power emitted by that source, at least from a circuit point of view, is proportional to its physical temperature, T sub n here in kelvins. Okay, so kelvins being temperature in Celsius plus 273. The noise power you get is proportional to the physical temperature of this perfect emitter object times the bandwidth over which you observe. Okay, our receiver over here has got some filter on it, so we have a certain bandwidth. And then multiplied by this constant, Boltzmann's constant, 1.38 times 2 to the minus 23, 10 to the minus 23 joules per Kelvin. So this formula is kind of a fundamental thing we use to exchange talking about watts of power to talking about equivalent temperatures. Okay, so a lot of times in this field, we're going to talk about temperatures, noise temperatures instead of noise powers. And so as we continue going through here, I'll be talking about noise powers in terms of temperature. In the microwave realm, we usually see that they're linear proportional. So, if you want to double the noise power, you double the corresponding temperature. And also bigger bandwidths mean that the same temperature object gives you more noise power coming out of it. Just according to this simple scaling here. Now, that's kind of a simple relationship, but in reality, we're interested here in the noise coming from the external world. Our receiver, our microwave radiometer up here in space, looking down at the Earth, is trying to receive the naturally emitted noise power coming from Earth's environment. And so that's a radiation process. So the reason we have this noise power is because matter radiates electromagnetic fields. Matter is made out of atoms and molecules which contain charged particles. Those charged particles are moving around all the time. And as charges move around, they radiate. It's there's a huge number of charged particles moving around. So you add up all those contributions, you get something that tends to look sort of Gaussian. And so that's the noise power we're talking about here. Our receiver has internal and external, anything made out of matter radiates noise signals. So our receiver that we build for our radiometer is made out of matter. It has an internal, the components of that are also radiating noise. That's an internal noise that's described by the noise figure of the receiver. But then we also have the external noise that we can receive through an antenna. And that's the part we're interested in here again. Now that external noise is a little bit more involved than just this simple, constant scaling between physical temperature and noise. And the way that's described is through the classic Planck's black body radiation law that tells you how the power from a piece of matter is radiated out into space. And the way that works is that an object, the noise fields emitted by an actual object that radiates out into space can be described in terms of its brightness. Okay, this quantity called the brightness. if you're familiar with electromagnetic wave theory, then when you study electromagnetic waves, you study plane waves. The power carried by plane electromagnetic wave is described by the Poynting theorem, and it's talked about in terms of the watts per square meter carried by an electromagnetic wave, a plane wave. So, a propagating wave, electromagnetic wave in space carries a certain power density, watts per square meter. If that electromagnetic wave passes through an antenna that has an equivalent area of some number of square meters, then that antenna will receive some number of watts. Okay, so typically for an electromagnetic plane wave that's propagating in just a single direction, we talk about its power density in terms of watts per square meter. But when we have a radiometer looking at the Earth over here, so suppose this is our radiometer here, we're looking, the Earth is out here somewhere. Our radiometer has an antenna. It's not just seeing a plane wave coming from one direction. It's seeing the whole surface of the Earth down here, which represents maybe a lot of different directions from the point of view of our radiometer. Maybe it's on the space. If you've ever looked at the videos from the space station, there's a camera on the bottom of the space station, and you get a field of view that includes many parts of Earth's surface. So we might be looking at the ocean over here and land over here, for example. So the total noise power we would get would be some coming from the ocean over here, some coming from the land over here, and so on and so forth. And we would be adding all that noise power up over our antenna pattern that's of our radiometer. So to describe that sort of brightness or power that's spread out, not only watts per square meter, but also spread out in angle, we use this quantity called the brightness. That's watts per square meter per steradian. Okay, so steradian is a unit of solid angle. So this quantity of the brightness is watts per square meter per steradian. In other words, sort of taking into account how much area an object occupies within our field of view. And it's also spread out in frequency because it's a noise power. White noise power is fairly flat in frequency. So this quantity called the brightness is watts per square meter per steradian per hertz. And the rest of the slide talks a little bit more about thinking about how to define steradians, but yeah, I don't want to get bogged down with that at the moment. So using that quantity, just looking here at this bottom equation, the noise power that our radiometer would receive actually is we had Boltzmann constant times bandwidth. Okay, so this noise power is still proportional to bandwidth. But now instead of just having one sort of object out there, we have to add up the brightness of the world out there that depends on angle, depends where I'm looking. We're going to add up the brightness out there as a function of angle weighted by the gain of my antenna pattern, which is also a function of angle, and add that up over all the angles my antenna is looking at. So again, this is noise power kind of spread out in angle that we're accounting for here. So that's what this brightness quantity kind of represents. And so the brightness quantity kind of physically is how it describes how noise power can be spread out in angle and look different depending what you're looking at out there in space. But we can further relate that to another temperature quantity called the brightness temperature, T sub B here. So um, there's the famous Planck's black body radiation law that basically is about this process. If you have an object that perfectly absorbs the power incident on it and perfectly re-radiates that as thermal noise, um, if you have a perfect absorber is called a black body because optically it would look black. Any light coming into this object doesn't get reflected, it just gets absorbed. So it's a black object. That kind of object has a particular relationship between its physical temperature, here written as T in kelvins, and the brightness, this quantity we've been talking about, that gets emitted from that object. So there's a one-to-one relationship between the physical temperature of a black body and the brightness that it emits. So that means in our equation, if we were only looking at black bodies out there, we could do some scaling of our equation, use this relationship. In the microwave region, this is a nonlinear equation, but in the microwave region, it turns out you can linearize it to this version. And so we could rewrite that previous equation instead of in terms of the brightness of the world out there, in terms of the brightness temperature of the world out there. So this brightness temperature is, for the moment, could represent the physical temperature of the black bodies out there in the world that are distributed in angle out there. Um, so if we were only looking at black bodies out there in the world, this would be the physical temperature of the black bodies. In reality, the world isn't made of black bodies. If we go to our ISS camera and look down at the world, it doesn't look all black. You can see the ocean, you can see the land, and so on. So those, since you can see something, they're reflecting, they're not black bodies. So the real world is not made out of black bodies. But we're gonna keep this equation and redefine this thing called the brightness temperature so that instead of being the actual physical temperature of the objects that are out there, it represents the physical temperature of a black body that would emit the same thermal noise power as the actual object that's out there. So it's sort of an equivalency or a scaling of the brightness temperature emitted by a real object, representing that in terms of the physical temperature of a black body that would emit that brightness, and using that to describe the noise power coming from the world out there. So that's kind of a long-winded explanation. Hopefully it was clear. Um, in the end, the main point of this discussion is that when we talk about microwave radiometry, we're going to describe the measurements made by a microwave radiometer in terms of the brightness temperature of the world. So microwave radiometers measure brightness temperatures. What they measure, in fact, is thermal noise power. Okay, there's just a receiver trying to measure the number of watts of thermal noise. But using an equation like this and understanding what the antenna gain pattern is of our radiometer and knowing what its bandwidth is and so on and so forth, we convert measurements of noise power to the equivalent brightness temperature and talk about the brightness temperature of the world as the science quantity that's the quantity we're trying to translate into the water vapor or land surface properties and so on. So one of the important things to understand about microwave radiometry is we're a community that talks about measurements of brightness temperature. And again, we want to measure these brightness temperatures, which are in units of Kelvin. We want to measure them very precisely. And, a typical Earth scene in the microwave frequencies, when you're looking at the Earth, the brightness temperature of the Earth can range from about 50 Kelvin, say, to about 300 Kelvin. So, and I'll try to explain a little bit more about that, why that's true later. So, if we think about physical temperatures of the Earth, what 273 Kelvin is 0 Celsius. So certainly some places on Earth, the physical temperature would be 273 Kelvin. Some places would be even colder than that, say 240, 250 Kelvin. And some places it's very warm, maybe it's 40 C some places. So there it's 300, the physical temperature would be 315 Kelvin. So Earth physical temperatures somewhere you could say 240 to 320 kelvins. So if the Earth was made out of all black bodies, you should only be measuring brightness temperatures between 240 and 320 kelvins. But in reality, in the microwave, what we measure is between about 50 and 300 kelvin, so much lower brightness temperatures. And that's because, again, the Earth isn't made out of black bodies. It turns out if you have an object that's not a black body, its brightness temperature is less than its physical temperature. And it can be much less than its physical temperature. In particular, the oceans of Earth have much lower brightness temperatures than their physical temperatures. We'll be saying more about that as we go. So as I was saying there, the uh, the brightness temperature of an object, which again is measured in kelvins, is not necessarily equal to its physical temperature unless you have a black body. Some places on Earth do look like black bodies, like a volcanic lava or something could look like a black body. The brightness temperature might be equal to its physical temperature. But other objects, the brightness temperature tends to be less than the physical temperature. And it turns out the brightness temperature that you get is more or less proportional to the physical temperature of the object. So here in this equation, T sub B means the brightness temperature of an object that you're looking at. T physical means its actual physical temperature if you stuck a thermometer in it. The brightness temperature tends to be less than the physical temperature. And the ratio of those two we call the emissivity of the object. Here written as E. This E doesn't mean 2.71828. It means emissivity of an object. And in radiometry, the emissivity is also an important thing. You can see from this equation, the brightness temperature that we measure from our microwave radiometer equals to the physical temperature of the object, if you stuck a thermometer into that object, times its emissivity. And so brightness temperatures tell us information about the physical temperature of the object, but they also tell us about the emissivity of the object. And, you know, to some degree, a lot of people aren't that familiar with microwave radiometry. You may be familiar with like IR infrared cameras and night vision cameras, things of that sort. So a night vision camera or an infrared camera is also measuring the thermal noise coming from some object. Um, and we kind of think of the infrared camera giving us an image of how warm is the environment, of the physical temperature. So in that case, in the IR and the infrared, we're kind of assuming when we think that the emissivity of these objects we look at in the infrared is very close to one, so that the quantity we measure, the brightness temperature, is basically equal to the physical temperature. But it turns out in the microwave that the emissivity is usually not close to one. The emissivity can be very different than one. And in the microwave, it's typically emissivity that's going to give us our science information. The physical temperature of the medium, we can usually figure that out from some other measurement. For example, from an IR sensor on a satellite is very good at measuring physical temperature of the environment. Or maybe we have a weather forecast or a climate model or something like that tells us what the physical temperature is. So it's really typically the emissivity that we're actually interested in the microwave that's going to give us the information about the scientific quantities we're trying to measure. Okay, so really a lot of the times we'll be interested in what is this emissivity, how does it behave, what are its physical properties. We'll combine measurements of brightness temperature with some other source of information about physical temperature, take the ratio of those two, and really what we're after is the emissivity of the environment. Okay, so now that we have some introduction about what is microwave radiometry, what are we trying to measure? We're trying to measure the brightness temperature. Um, the measurement we get is basically, the brightness temperature of the world out there integrated over the field of view of our antenna represented by its gain pattern here. Okay, and these limits here mean integrated over all possible look directions. But typically we want to have a high gain antenna. So we want the gain of our antenna to be high so that we're only looking in a particular place. So in other words, this gain function would be big only for some narrow range of angles. It'd be zero everywhere else. So we could approximate that we're really just looking one place at the brightness temperature in one particular place. Um, in addition to that, this equation is telling us that this is sort of like what we measure. We're trying to get the brightness temperature of the world out there. It turns out there's we also measure internal noise. We get some contributions from the physical temperature of the antenna if it's lossy. So in a radiometer, you want to have a very highly efficient antenna, an antenna that has almost no loss to get rid of this term or make this term very small. You want to have a low noise receiver so that you're mostly measuring external noise and not internal noise. You want to have a high gain antenna so you can sort of tell where the radiometer is actually looking. And that's what this slide is about, a little more detail in these comments here. Also, we want to measure we're trying to measure the naturally emitted noise from the environment. So we don't want to be picking up somebody else's transmitted signals. If we're trying to measure the noise part, not the signal part. So we want there to be no signal part, just noise. So that means we want to perform radiometry in protected bands where people aren't supposed to be transmitting. Otherwise, we'll be getting the transmitter's signals instead of the natural thermal noise that we're actually trying to measure here. So that's why radiometry is typically performed in protected bands where, definitely requires a lot of spectrum management to be able to make these measurements at all. If we try to measure in bands where there's a lot of use by communications users, typically it would be very difficult to get any of this background noise scientific information from that part of the spectrum. Although there's certainly a lot of research in trying to coexist, trying to figure out ways to allow radiometry and communication users to work together. But generally, certainly in microwave radiometry, we prefer to have no one else using the same band we're trying to do our radiometry in. It means also that we want tight filters on our radio. We want our radiometer band to look only at a very certain part of the spectrum where no one else is supposed to be transmitting. So our receivers should have well-defined filters, try to roll off very rapidly, have low gain outside of the radiometer observing band, and so on. So there's a lot of basic receiver design sorts of issues here that I won't have time to get into today, but those are important aspects of radiometer design as well. Filter design is definitely a important aspect. Um, any questions at this point? I'm happy to take any if there's any. If not, so again, sort of a cartoon here. Our radiometer is up here in space. Here's the antenna. It's looking down at Earth. We're trying to measure the properties of Earth's surface or atmosphere in a particular place, like we would like to make a map eventually from our radiometer measurements of what's happening at this place on Earth and that place on Earth. So, you know, we want our antenna pattern, this sort of region here is meant to indicate the extent of the antenna pattern. And so if we map that antenna pattern onto the Earth's surface, that sort of determines how big a place on Earth's surface that we're looking at. So the tighter we can make this region here, in other words, the higher gain antenna we can have, the smaller of a pixel size you could say we'll have in our map on Earth's surface, so this finer spatial resolution we'll achieve. I should point out that, if you're interested in antennas, you know that antennas have a main beam. They can have side lobes. We don't want to have high side lobes because we want to think we're looking over here and not receiving signals from somewhere else. So high gain antennas are useful in radiometry. High efficiency antennas are useful in radiometry. Was there a question?
Yeah, we've got one in Charlottesville.
Could you go back to the equation on slide 11? What's V there?
Yes, sorry, I don't really have time to get into great detail here, but this symbol means the efficiency of the antenna, the radiometer antenna. So
Okay.
if we make the efficient, if we have a perfectly efficient antenna, nu is 1. So this quantity ranges between 0 and 1. 0 means a very bad antenna. 1 means a very good antenna. So we would like to have nu close to 1. TP here means the physical temperature of the antenna. If you stuck a thermometer in the antenna. So you can see if nu is equal to 1, that term goes away. If nu is small, then the thing we're measuring is this external noise we'd like to get, plus contributions from the physical temperature of the antenna. In other words, our measurement's acting like a thermometer on the antenna, which is not what we're trying to do here. So we would like to have nu be close to 1 to get rid of this term.
Okay, thank you.
Sure. All right. Let's see. So as I mentioned, we want to have high gain antennas. The higher gain we can make, the finer spatial resolution we'll get. We want to operate in protected bands. So here's a list of some of those protected bands throughout the spectrum. So if you're a radar person, this band is called L band. So there's a couple in L band. There's some in S band. Here's a C band one, X band, and so on and so forth. This 23 gigahertz line or spectrum allocation is important in radiometry because it turns out water vapor in Earth's atmosphere has an absorption line. So this is very useful for sensing water vapor properties. Also near 60 gigahertz, this 52 to 54 is important for sensing temperature profiles in the atmosphere because this is near an oxygen absorption line in the atmosphere. Some of these bands are near absorption lines, others aren't. But again, we want to have protected bands to be able to measure this thermal noise power without having to worry about other transmitters interfering. And of course, this is all managed by the ITU, by a regulatory process. It continually evolves in time. Certainly, the radiometry community is very interested in protecting these bands. so that we can continue to perform high quality radiometric measurements in these bands. And it's important to be able to maintain the ability to do this sort of science and climate and weather measurements that we're talking about. So as I mentioned, as our radiometer flies over the Earth, it's going to be making measurements continuously, and we'll have our integration time. Remember, I talked about the integration time, how long we're going to average before we report an average value. So as our spacecraft flies along, it's continually making measurements. It's reporting a brightness temperature periodically, and typically this is at timescales of like 10 to 20 milliseconds as the spacecraft flies. And so the amount of distance that we travel in that integration period, as well as the footprint of our antenna, the beam width of our antenna projected onto the ground, determines the spatial size of our region that we measured, the pixel size in our image if we were to make one. And, there's a lot of interest in spaceborne sensors and what kind of images you can make from spaceborne sensors. Like if you look on Google Earth, you can see optical images from space that are sort of at the sub-meter or, resolution, which is very impressive resolution to obtain from, orbits that are in the hundreds of kilometers away. You may have also heard of synthetic aperture radar, SAR here, that can produce very high resolution radar measurements from space, sort of on the even sub-meter scale resolutions. Those all are, optically, you can get very fine precision with telescopes. With radar, there's a trick to how you form that high resolution. But in microwave radiometry, those tricks don't apply. And if you study antennas, you know that to make a high gain antenna, the size of the antenna needs to be large compared to the wavelengths, the electromagnetic wavelengths. And so in the microwave frequencies that we're talking about here, when I say microwave, I mean sort of between like, let's say 1 and 100 or maybe 200 gigahertz. That also covers what some people call the millimeter wave region. So if you think about those wavelengths, especially at 1 gigahertz, say the wavelength's 30 centimeters, if you want to have an antenna aperture that's very large compared to the wavelength, it's going to be a big antenna from space. So certainly, many microwave radiometers are deploying large antennas in space, sort of to the tune of sometimes 1 meter antenna diameter, sometimes getting up to 10 meters antenna. We would like to have 10-meter antenna diameters in space. And because we can't do this additional processing tricks in radiometry, we're basically stuck with the resolution that you get on Earth's surface depends on how far away you are, what your orbit is of your satellite, and what the gain of the antenna is. So you just take the beam width of the antenna, project it from that distance onto the ground. That's your footprint. That determines the pixel size. So because our antennas in space are decent, they're high gain antennas, but they're not as high gain as an optical telescope would be. So typically radiometry, the sort of spatial resolutions we're getting on the ground are on kilometer scales or coarser. Okay, sort of 1 kilometer in some cases, 5 kilometers, 10 kilometers, sometimes even 100 kilometers. Okay, so these are not sensors that are for reading the postage stamp from space. These are sensors that are for getting large scale information about Earth's surface on scales sort of, 1 to 10 kilometers pixel size. Okay, but if you think about that, those pixel sizes are certainly very useful. The Earth itself contains very, very many 1 kilometer, pixels of 1 kilometer on the side. So even with that sort of coarse resolution compared to optical sensors, you can still get a very large number of pixels across Earth's surface for talking about weather, oceans, atmosphere, and so on and so forth. So even with this coarse resolution, again, still very useful, impactful measurements. And of course, this I'm talking about from space here. If you deploy on an airplane or close to or UAV or from a tower or something, then of course the resolution gets finer as you come closer to the thing you're looking at. So that's another thing to understand about microwave radiometers. There is a kind of radiometer called a synthetic aperture radiometer. This is kind of similar to the interferometers used in radio astronomy, where we use a phased array. Instead of just having one large reflector antenna, we have a lot of little antennas, make a phased array out of those. But it's still true for that kind of antenna that the spatial resolution you get depends on the overall size of the antenna. So, you don't get better spatial resolution from this kind of synthetic aperture radiometer unless you make the aperture larger. But the benefit you get from it is that you can beamform to look in many directions at the same time. Instead of just having an antenna pointing in one direction, you can post-process the measurements to form measurements looking at many angles simultaneously, just basically like a radio astronomy telescope also does in many cases. So if you hear the term synthetic aperture radiometry, that's what it refers to. And currently in space, we have the European Space Agency's SMOS radiometer, Soil Moisture Ocean Salinity Mission, operates a synthetic aperture radiometer that has a phased array that beamforms, produces many look angles simultaneously. Um, okay, so that's sort of the basic properties of the spatial resolution. Now, as I mentioned, we're trying to measure the brightness temperature of the world out there. We want to measure it to high precision. And again, the precision that we get depends on this product, the time bandwidth product. And sort of lingo of the radiometer world, it's a notation we use is that we talk about that precision. How precisely is one, after I've done my integration over one footprint on the ground here, how precisely is my estimate of the brightness temperature measured? We call that the noise equivalent delta temperature. Okay, kind of a strange term, but this is what radiometer people, the notation we use. So this is abbreviated NEDT. And what it means again is the precision that we expect to get from our single integration time measurement of the brightness temperature. So again, this quantity is inversely proportional to the square root of the time bandwidth product. Okay, so tau here again means as my radiometer is flying along, it takes some amount of time to make the measurement. It's going to tell me, okay, I got this for the brightness temperature after it measured for some amount of time. That's what tau is, the integration time. And B here is the bandwidth over which I'm operating. And so again, larger bandwidths, longer integration times give me more precision in measuring the brightness temperature. Now, this is also proportional to the internal temperature of my receiver. That's what T-sys here means. It's, do I have a good noise figure receiver or a bad noise figure receiver? And TA here means, this quantity that combines the actual brightness temperature I'm trying to measure and any losses from my antenna. Okay, so the precision I get also depends on the scene that I'm looking at, but definitely very sensitive to this time bandwidth product. So this is why radiometers want spectrum access. Okay, we want larger bandwidths. We want longer integration time. Now, the integration time for a spaceborne radiometer, if you think about that, my spacecraft is flying at a velocity, and in low Earth orbit, these velocities are something like 6 kilometers in a second. Okay, to get into orbit, you need a rocket to accelerate you to a very fast velocity. So my low Earth orbiting satellite's moving about 6 kilometers a second. It has an antenna on it that's looking at the ground. That antenna makes some footprint on the ground. And as I fly, that footprint is moving along with my radiometer. So I wouldn't want to integrate, longer than it takes in time to move through a footprint or maybe half a footprint. So there are some other constraints on integration time based on the satellite motion and how it observes and so on, as I'll talk about a little bit more in a minute. But the bandwidth is set by what spectrum allocation I have, which band I'm working in, and so on and so forth. Now, as I said, the brightness temperature of the Earth sort of ranges in the 50 to about 300 kelvins, let's say. So as my radiometer, if it's working right as I fly over the Earth, I'm going to see brightness temperature going from sort of 50 to 300. As I'm over the ocean, it'll look cold. As I'm over the land, it'll look warmer. If it goes over the cryosphere, it may look some colder than that. But then again, I'm going to try and translate that brightness temperature measurement into an emissivity of the Earth's surface or of the atmosphere. And using that emissivity, I'm going to translate that into um, various properties of the environment. And again, the precision with which I measure the brightness temperature is going to translate into the precision I get in those products. And to make a long story short, it turns out the precisions I would like to get typically are 1 Kelvin or better. And even now, for some products, getting down to 1/10 of a Kelvin. So I would like this number over here to be something like 0.1 to 1 kelvins, the precision of my measurement. Okay, so again, if I plug in some, this is, let's say this is between 50 and 300. This depends how good my receiver is, but maybe it's on the order of the 150 to 300 Kelvin or something. So this is sort of, let's say, 300 Kelvin up here to 500. So then if I want to have 0.1 Kelvin, I can work out, for a given integration time, what bandwidth do I need? And again, the more bandwidth I can access, the finer precision I'll be able to get. But it is, from I'm talking to you from a point of view of a radiometer scientist. I would like to have high precision in these measurements. From the point of view of a communication system person, you could say, wow, that's a lot of bandwidth that I'm translating into this one number. I had a big bandwidth I measured for, let's say, 20 milliseconds to get this one very precise number. But my communications users could have transmitted a very large number of bits during that same time interval. So certainly there's you know, uh, we're all interested in multiple applications of the spectrum. And, these sorts of analyses can help us understand the relationships between the science performance you could achieve and, what you could have achieved from a communications point of view. Okay, so here's a little example of that. Let's suppose we had a radiometer. It was operating in this protected L-band part of the spectrum. Okay, so currently in orbit we have NASA's Soil Moisture Active Passive SMAP mission is measuring Earth's soil moisture and many other products as well. Operates in this band using more or less, not quite, he actually uses 24, not 27 megahertz. So here we said, let's suppose we use 23 megahertz in this protected band. This is a band that's supposed to be entirely protected. Okay. Let's suppose that our receiver had a certain noise figure. We had 100% efficiency. We could ask ourselves, what integration time do I need if I want to get 1 Kelvin precision? And the scene that I'm looking at is 290 kelvins. In other words, the Earth brightness temperature was 290 kelvins. So this information is enough to use that formula. Now we have to translate noise figure, which we haven't talked about, but we can translate receiver noise figure into that system temperature quantity that was in our previous equation. It turns out it's also 290 kelvins here. We said the antenna was 100% efficient, so we don't need to worry about that antenna physical temperature quantity. We take this information, we plug into this equation. We know the bandwidth was 23 megahertz, so we can solve if we want the precision to be 1 Kelvin. You need about 15 milliseconds of integration time, which is close to what the SMAP radiometer uses as its integration time. So that's an example of a sort of semi-realistic set of numbers there. Um, so far I talked about these radiometers. Radiometer is just a single footprint, like we have an antenna looking a single direction and it orbits and the footprint slides along with it. There are certainly radiometers that act like that. Those are called either nadir looking or push broom radiometers. Okay, I think I have some pictures here. A nadir looking radiometer is one that just looks straight down. And as it flies, the footprint just moves along with it. And so over time, you'll trace out a track of pixels on the ground. So it's just a track sort of imaging thing, making a line of pixels. There's certainly many radiometers in orbit working like that. Those actually typically fly along with radar altimeters. Okay, instruments that also measure range to the ground. The radiometer doesn't measure range. It only measures the thermal noise that it sees. It's incapable of measuring range. A radar can measure range. It's not unusual to fly a radar altimeter and a radiometer together, where the radar is transmitting pulses, measuring the time delay to what comes back to get range to the Earth's surface. And the radiometer that flies along with it is measuring in a different band to measure the water vapor on the path, because that water vapor causes a delay for the radar altimeter that needs to be corrected. to get a precise range measurement. And these radar altimeter measurements in earth science are used to measure, changes in heights of Earth's surface, in particular sea level rise. So, a lot of the information we have about sea level rise comes from radar altimeter missions that are co-flying with microwave radiometers that implement this water vapor range correction. So that's one application of a radiometer we haven't really talked about very much yet, but there's certainly many in space operating like that. The push broom is kind of similar, except instead of looking straight down, we might look a little off to the side. So as we fly the pixels a little off to the side, and we would still just be making this line of measurements, a line of pixels. But sometimes we might even, instead of just having one antenna on our spacecraft, we might have three or more than that, all just looking at different spots on the ground. So we can put multiple spots together to make this multiple pixels that fly out, as we fly along, flying this way, we trace out multiple lines of pixels to form sort of an image here. So that's whether we had one or multiple pixels, they're all called a push broom sort of geometry. But when we have, and push broom just sort of means like we're sliding the broom along the Earth's surface to map out these pixels on Earth. The previous NASA Aquarius mission operated like that. That was a mission for measuring sea surface salinity. As we do this for remote sensing instruments in space, so as the satellite is flying, it's sort of flying this way, along which we have multiple pixels. We also talk about, if we're making an image, not just one line of pixels, but multiple lines of pixels, what is the width of that line? Here it's labeled as 390 kilometers. That's called the swath of the instrument, the swath width. Okay, so for example, in this picture, the swath width is 390 kilometers, 390 kilometers, because as the satellite flies along, you're getting an image that, spans 390 kilometers. Well, that's a push broom sort of configuration. There are radiometers operating like that. But in addition to this sliding, moving along as you fly, there are other radiometers that, as the satellite flies, move the antenna around. The antenna is not just in one fixed position, it moves around. So those are called scanning radiometers. And there's a couple of different scan patterns that are used, one of which is called cross-track scanning. Okay, so cross-track scanning looks like in this picture. So our satellite here is flying in this direction, okay? And so as we fly along, this line of this set of pixels here is going to be, moving along, going this direction. But as we move, we take our radiometer antenna up here on the spacecraft and we rotate it back and forth in a direction perpendicular to the direction of flight. So that's called the scan direction. And so we scan our antenna. This is called a cross-track scan. And so when the antenna is scanned over this way, it looks over here, and then as time elapses, it scans closer in and so forth, and then it scans further out. So we get this creates a swath then. So we have a swath of pixels that are created as we fly, so we get an image to come out of this. Now, in a cross-track scanner, it turns out, as you scan further off nadir, the footprint, because of the projection on the ground, gets a little bit bigger. So this doesn't have a constant spatial footprint, but that's something we can be aware of. And, as we use these data for our science observations, we can account for that sort of thing. So that's a cross-track imager. A lot of times these are used for primarily atmospheric applications. So the AMSU sensor in orbit is an example of that. The ATMS is another example. So that's one type of scanning. Another type of scanning is called conical. So here's an example of that. SMAP is a conical scanner. There are many conical scanners in orbit right now. In a conical scanner, it's sort of like a push broom. We're looking off at an angle here. So here's our radiometer pattern looking off at an angle. The spacecraft is flying this direction, okay? But instead of scanning back and forth cross-track like is shown sort of here, we take our radiometer, point it off at an angle, and then spin it around in a circle. So then the set of sort of look angles created by that circular rotation makes a cone. Well, that's why it's called a conical scanner. And in this case, every place that we're looking has the same incidence angle. Unlike this one had varying incidence angles onto the ground. every angle here on the Earth's surface is the same because this is spinning around in a circle. And we get measurements across the circle. Our antenna pattern determines the spatial footprint, but we sweep out a whole bunch of spatial footprints as we go here. So, and the span, the diameter of the circle is the swath of the image that we've created in the end. And, as we keep going, we'll make more and more circles. Sometimes we may be able to observe over the entire circle. Sometimes we may observe only over part of the circle, but both of those are called conical scans. And so there are many radiometers operating with conical scan. Certainly, in a lot of remote sensing instruments, we would like to have a large swath width. Okay, because if you think about it, you would like over the course of many orbits that you cover a large fraction of Earth's surface. Your radiometer in space from one look, from one orbit, is not covering the entirety of Earth's surface. And this is an illustration of that. You can see here, you know, from low Earth, many of these satellites operate in low Earth orbit. And in low Earth orbit, you're making a complete orbit around the Earth in something like 90 minutes. You're moving about 6 kilometers a second. In 90 minutes, you make a complete orbit of the Earth or something like that. And so as we make one orbit, the width of the image we're creating is indicated by the width of these green traces here. So this would be our swath width. And then as we come around for the next orbit, the Earth rotated slightly during that amount of time. So our next orbit will trace out a different place on Earth, and the next orbit a different one, and so on. It's sort of like we have an orange, and we're peeling the orange with different slivers, and we'd like to have all of our slivers add up to cover the whole orange over some amount of time. And you can see that we'll have a better chance of doing that the wider our swath width is. As we peel our orange, we want to peel it in big chunks of orange rather than small ones so that we don't have to do too many orbits to cover the whole Earth. But certainly if you start putting all those considerations together about how fast does the spacecraft move, how long of an integration time do I need, what's my spatial footprint, and so on and so forth, there are constraints in the final system that make it such that, a good radiometer, a conical scanning radiometer swath width is typically about 1,000 kilometers. And with that sort of swath width, we can get global coverage in about 3 days. In other words, for no point on Earth's surface will you have to wait longer than 3 days before you get a second measurement. It's also true that we tend to, if you think about your spacecraft orbit, if you want to cover the whole Earth and the Earth is rotating below you, it makes sense to put your orbit such that it goes close to over the pole if you'd like to cover all latitudes or close to all latitudes. So many of our spacecraft operated, in orbits that go close to going over the pole if you want to get full Earth coverage. And if you think about that, as I come back and forth across different orbits, well, every orbit's going to go close to the pole. So I'm going to have very frequent revisit over the poles because every orbit's going to go over the poles. And the place where we need to wait 3 days to recover everything is close to the equator because that's where I have the most real estate that I need to cover. Up at the poles, there's not much real estate to cover. At the equator, there's a lot of real estate to cover. So, my coverage period, when I say 3 days coverage, it means that's the longest you'd have to wait. And typically that would be near the equator. At the poles, you could have multiple observations per day. Now, there are some radiometers that are not in polar orbits because they may be only focused on some particular areas. For example, those interested in observing cyclone sorts of behaviors and so forth would be have orbits inclined to lower inclined orbits because the cyclones are all at lower latitudes. They don't go up to the poles. So you don't need to cover those if you're trying to study cyclones. And so there are different orbits for different radiometer applications and different mission goals, but many of them are operating in orbits that go close to the poles and have this property of frequent revisit near the poles and less frequent revisit near the equator. So yeah, those are different scan types, different properties of radiometers. And again, some are focused on measuring the surface, some are focused on the atmosphere, some are doing both. There's the term a sounder. when you hear of a radiometer sounder or a sounder means in the radiometry world that we're trying to measure atmosphere properties, and often atmosphere properties as a function of altitude. For example, the temperature profile of the atmosphere. The temperature is a function of altitude. So that's a term that you may run across if you get involved with radiometry. Imagers are usually looking at the surface and typically, trying to make maps so they'd be more on the scan type, cross-track scan or the conical scan rather than the push broom type. Polarization also matters in radiometry. We don't have time to talk about that. Polarimetric means you try and use some of the polarization properties of the electromagnetic fields to get more information on what you're observing. Again, don't really have time to talk about that, but that's a term that you may come across. Sort of reviewing. I don't really have time to talk about, as I said, the radiometer measures brightness temperature, which is a function of physical temperature and emissivity. Usually it's the emissivity that we're interested in. The emissivity properties of a scene come from its ability to, the properties of that material in terms of reflection and transmission. So for those of you who study electromagnetics, you learn about reflection coefficients of the Earth. If you study propagation, you learn about atmospheric absorption. So emissivity is related to how much power an object absorbs when it's illuminated, how absorptive it is. And as I said, a black body absorbs perfectly. It has an emissivity of 1, but other objects don't absorb perfectly, so they have emissivity not 1. So these sensitivities that are shown here basically come from those sorts of properties about how do different materials in Earth's environment absorb or reflect or scatter electromagnetic energy. And sort of a summary, again, not getting into the physics of this, which I'm love to work on and happy to talk about that, but didn't really have time to get into details here. If you look over the ocean surface, those physics wind up giving you these sorts of sensitivity curves versus frequency. That, for example, the permittivity of the seawater of the ocean versus frequency is such that the brightness temperature is sensitive to the salinity of that seawater. How salty is the seawater down here at lower frequencies like 1 gigahertz? Okay, that's kind of a surprising thing, and basically, optically, you could never measure the salinity of the seawater, but with microwaves, you can, and you can do it from space, and it's being done right now by the SMOS and SMAP missions. This is sensitivity to the physical temperature as I said, brightness temperature depends on physical temperature and emissivity. It turns out the physical temperature winds up dominating that in some portions of the band, near the C-band in particular. This is sensitivity to roughness, okay? The emissivity of the ocean surface, how much it absorbs or reflects, depends on wind speed because winds create roughness on the ocean, which translates into absorption and reflection. So you have a sensitivity to wind speed. Earth observing radiometers are used routinely to measure wind speed and actually wind direction also over the ocean. This is an atmospheric property, the water vapor. As I mentioned, near 23 gigahertz, water vapor in Earth's atmosphere absorbs microwave energy. And so using that fact, you can get a sensitivity to water vapor in Earth's atmosphere. And a lot of radiometry is used for measuring water vapor in the atmosphere. Clouds also get involved. And there are if you continue to higher frequencies up to 60 gigahertz you would find a sensitivity to atmospheric temperature that's used in temperature profiling. And so on, continuing to other absorption lines, like there's an oxygen absorption line at 118 gigahertz, water vapor line at 183 gigahertz, water vapor line at 325 gigahertz. A lot of atmospheric radiometry is done at frequencies sort of 100 to 300 gigahertz. But things where you tend to see the atmosphere predominantly, it's at these lower frequencies that I've shown in this plot where we tend to see the surface more. So that's over the ocean. Here's over land. Similar plots over land versus frequency for these are sensitivities, like how sensitive is my brightness temperature to that particular parameter. Water vapor is shown here again, same plot, basically. Cloud water is shown again. But we've got soil moisture. It's a little bit hard to tell, but soil moisture is this curve that peaks down here. So lower frequencies in the microwave band, C band, L band, and we discussed going into even lower frequencies these days where you would have to do spectrum sharing, are very sensitive to soil moisture. This is vegetation. Sensitivity to vegetation tends to increase with frequency. There's sensitivity to surface roughness. You can see from these plots that, if we just measured at one band, suppose we just measured at 10 gigahertz X band here. Well, X band is sensitive to wind speed. It's sensitive to sea surface temperature. It's sensitive a little bit to clouds. It's sensitive a little bit to water vapor. It's sensitive to a whole bunch of things. So if we were just to make one measurement at X band, we would probably be getting the combined effect of all these factors, which may be hard to separate them out. So it's typically true in radiometry, especially for ocean observations, that we measure at multiple frequencies. A lot of Earth observing radiometers will have channels at C band, okay, X band, one near 18 or so, one near 23, one near 30, 36 or 37. And by combining the measurements of those simultaneously and understanding how each of these is sensitive differently to these different factors, we can separate out all those factors and measure all these things simultaneously. Okay, and that's why, way back here at the beginning, we had this chart of radiometer missions, and you could see there were different missions were using different combinations of channel frequencies measured simultaneously to try and separate out these different geophysical factors. All right, and it's typical, again, it's typical to include 20, if we're trying to get water vapor. So any radiometer you see using channel near 23 gigahertz is trying to measure water vapor. But even at 23 gigahertz by itself, the sensitivity is high, but we're also even there sensitive to roughness, sensitive to other factors. So if we have 23 gigahertz, we also need to combine it with some other frequency, typically 18 or 30, 31 or 36, that's not as sensitive to water vapor. And by combining those two, we can separate out the water vapor or cloud liquid water. Again, these are oxygen absorption lines, which are used for temperature profiling. So certainly there are certain frequencies in radiometry we want to use because Earth's atmosphere absorbs at those frequencies, gives us this capability of making particular atmospheric property measurements. But other frequencies, these sensitivities are pretty broad. For example, the sensitivity to soil moisture is higher at lower frequencies, but it's pretty broad. So we could use lots of frequencies to try and sense Earth soil moisture. We could use lots of frequencies to sense vegetation. So there are varying degrees to which you have to be in a particular band to make a particular measurement. But certainly we want to be in protected bands. So even if we have a broad sensitivity, we would prefer to operate in the protected band, which is why, for example, at L band, the 1400 to 1427 megahertz band is what's used in practice. Maybe I'll stop there a second to see if there's any questions at this point. Just a few more slides to go here.
Sorry, we problem unmuting for a moment, but we have a question here in Albany. Yes.
Yeah. Can you talk more about the sounder satellites? What does the atmospheric properties mean?
Yeah, so I'll repeat for everyone. If you could talk, Joel, more about the sounder satellite and what do the atmospheric properties mean? So what more specifically about the atmosphere do they measure?
Yes. So certainly one property of the atmosphere. So microwave radiometry, let's say below let's say 100 gigahertz. The properties of the atmosphere primarily that are measured are the water vapor content. How much water vapor is there? Is it humid or is it not humid? And so that's one property. And typically we'd be using 23 gigahertz in combination with some other frequencies to try and measure that. Typically that measurement also would be the integrated water vapor content. So in other words, we'd take a column of atmosphere all the way from the surface to the top of the atmosphere and just add up the total amount of water vapor in that column. That would be our measurement. We wouldn't have information about water vapor versus altitude, but typically water vapor is located at low altitude. So it's a single integrated water vapor content measurement. If we operate near oxygen absorption lines, like 60 gigahertz, there we're trying to measure the temperature of the atmosphere as a function of altitude. So in other words, we're trying to see what's the temperature a few kilometers above the surface. What's the temperature a few more kilometers above the surface? We're going to measure a temperature profile, the temperature versus altitude. So when we say sounder, sounder tends to imply that kind of measurement, making a measurement as a function of altitude. And below 100 gigahertz, it would be a measurement of the temperature, physical temperature of the atmosphere as a function of altitude. So we're translating brightness temperature measurement into physical temperature measurement as a function of altitude. And the way you make the measurement as a function of altitude is um, the 60 gigahertz absorption line in the atmosphere is a very sharp line. Okay, the closer you come to 60 gigahertz, the more attenuation, the more opaque Earth's atmosphere is. And that's because the oxygen in Earth's atmosphere absorbs microwave energy really well there. If you move a little bit away from that peak of the absorption line, it's still opaque, but not quite as opaque. Until you move far enough away from the line center, there the atmosphere becomes transparent again. So in a sounding radiometer, we're making measurements, brightness temperature measurements of the atmosphere as a function of frequency at multiple frequencies near the absorption line, some closer to the line, some further from the line. The frequencies closer to the line peak, the atmosphere is very absorptive. So they're only going to see the noise power coming from a high altitude portion of the atmosphere because everything else is very attenuated by the time it gets there. Our radiometer is looking down and receiving these emissions coming from the atmosphere. As you move a little further away from the absorption line, the atmosphere is a little more transparent, so you can see a little bit deeper in the atmosphere. If you move a little bit further away from the peak again, then you can see a little bit deeper. So by making multiple measurements as a function of frequency near the line, we're seeing information from different depths in the atmosphere. And putting all that together, we can get a measurement of temperature profile, temperature versus altitude in the atmosphere. So that's what a sounding measurement refers to. If we go to frequencies above 100 gigahertz, there you can start to see absorption lines from other trace gases, other types of, below 100 gigahertz, it's primarily water vapor and oxygen are your two absorbing gases. If you start going above that to, in sort of semi-terahertz frequencies, you can find other gases, trace gases in the atmosphere that cause absorption, and you can use those sort of hundreds of gigahertz frequencies to try and sense properties of those.
Thanks. Are
Yes.
there any more questions from other sites?
Thank you.
I did have one question just in terms of the applicability of these measurements. So what if you think about weather prediction as one of the applications of these measurements, what percentage of our weather prediction actually comes from the data that you take from space versus, are there other instruments that figure into the picture?
Yes, of course. Yeah. So certainly, everybody wants to know the weather, right? And during this span of my lifetime, the weather forecast has improved a lot. But certainly, there are many sensors and many models that go into predicting the weather. It's certainly a very complicated process involving a long history, many areas of investigation. We certainly have when you watch the TV weather report, you sometimes will see optical images from space of the Earth showing the cloud patterns. Optical images can see clouds, and where clouds are is certainly important information for weather forecasting. We certainly use radar systems on the ground. Weather radar is mapping precipitation, very important local high-resolution measurements. But if we're interested in measurements of the entire atmosphere and even going to higher altitudes, the microwave radiometers are some of the most impactful measurements on the forecasts that are out there. And it's been shown, the way weather forecast works right at the moment is you have a model that tries to describe physical processes in the atmosphere and how they evolve in time. Actually, you have an ensemble of models because there's a lot of uncertainty in this. So you don't just have one model that everybody trusts. You have a lot of different models of different ideas about how this model should work. You run all of those, and the model as it runs tries to ingest whatever information it has about the world out there from whatever source it can access, including microwave radiometers, but including optical satellites, including in situ measurements, including everything it can find. And all that information gets combined together, ingested into this model that tries to put it all together and make some forecast out of this. So it's really hard, it can be difficult to say this particular sensor is doing this or that. But you can run tests in which you create forecasts where you use the data of some particular input or you didn't use that data. And it's been shown not using this sort of microwave radiometer sounding and water vapor data does result in a significant degradation of the forecast accuracy. So it's certainly an impactful sensor and therefore, very relevant to keep as part of our information about the environment.
Thanks.
Yes. And certainly a lot of science, a lot of radiometer missions begin with some concept, oh, this is a measurement we could make with this type of sensor. And the goal of that work is to have that data eventually assimilated into the forecast or climate model and to make an impact on the accuracy of the prediction of that. And that's been shown not only for the atmospheric products, but also for some of the surface products as well.
Okay, great.
Yeah.
Any more questions? We'll certainly keep you for questions in the end as well.
Yes. Now, let me go ahead and wrap up this. So the last few slides are about spectrum issues. I hope I've given you some idea of how radiometers work and what they're used for and so on. From a spectrum point of view, they're passive. They don't transmit anything, so they can't interfere with anybody else. They can only be interfered with. You can have as many radiometers simultaneously operating as you want because they don't transmit anything. They only receive. But, if we're talking about sharing a spectrum, an active user doesn't know when a passive user is there typically, and so it definitely has the potential to interfere. The radiometer, an old school radiometer would always just be integrating the power of whatever was there and couldn't tell if it was a transmitter or not a transmitter. And so therefore it was could be very much uh, subject to interference from active users, and which is why we need the spectrum allocations to preserve them. And then from the radiometer world, we would call the presence of any active user in our radiometer band an interference, radio frequency interference, or RFI. And as the spectrum becomes more crowded and more in demand, then certainly coordination is important. Certainly if we want to preserve our applications of the radiometer data, we need it to be uncorrupted. If we thought we had a good measurement of the natural noise coming from the scene, and actually we got a measurement of the noise plus somebody's signal, that signal is going to bias our result and it's going to mess up our ability to have an accurate forecast and so on. So it's important to preserve the accuracy of these, and the ITU does that. That's the forum through which the regulations are discussed and evolved and so on. And so certainly uh, the passive microwave community tries to maintain a presence with the ITU through various organizations to influence that and have a voice in spectrum allocations. If you look across the spectrum allocation table, you can see there's a whole lot of applications. We're talking about here about the Earth Exploration Satellite Dash Passive Service, which typically, is aligned with the radio astronomy service. They'll both typically have an allocation in the same place since both passive can't interfere with each other. And we've talked about where they exist. If you think about your radiometer again, we want to have a tight filter of our radiometer. If we're in a protected band, nobody else is supposed to transmit. We'd like to have our radiometer filter on the front end of our receiver be tight so that it's not going to receive out of band. Transmitters operating out of this could interfere with us if our filter was too wide, like this blue one here. So we want to make narrow filters, which is going to limit our bandwidth and therefore precision, but we need to operate inside of our protected bands. If there's a source out here, it could interfere with us if our filter was too wide. You could have sources operating out of band that don't intend to radiate over here, but their filters aren't good either, and so they unintentionally radiate into this band, which causes interference. And again, the regulatory process and design of products and so on is supposed to account for these sorts of things. When we think about the presence of a transmitter in a radiometer band, for us, again, we think about brightness temperature. What's the brightness temperature that we receive? But we can translate the power, in a communication system, we think about what's the number of watts received, and it follows the Friese transmission formula. But we can transmit the Friese transmission formula into error in brightness temperature, just using some of these basic relationships for a communication system. And it turns out, the error in brightness temperature that I get in my radiometer footprint depends on what's the total number of watts of transmit power in my footprint that I receive. And so that means, it's not just one transmitter that matters. It's the total number of transmitters within my radiometer footprint or even in my radiometer antenna side lobes that can contribute here. So it's not just one transmitter that may be a problem. It might be a may not be one big transmitter that's a problem, it may be a whole bunch of little ones that are unintentionally radiating small amounts of power that bias my radiometer measurement. So, again, the regulatory process is very important here, and accounting for this, when something's approved, what is the future amount of aggregated total power emitted that's going to occur from that approved system? Not just one device, but an accumulation of many of them inside of a radiometer footprint. Here's some examples of interference that have been observed by radiometers. Quick picture. This is just in the bands 6 to 19 gigahertz by one instrument, particular radiometer reported in this paper here. There are many papers about radiometry, RFI observed by Earth observing radiometers in protected bands. And also, sometimes we don't necessarily observe only in protected bands. So, some of the things seen here are not necessarily prohibited, but they're just interference that radiometers saw. You can see there are lots of different sources of interference occurring. And, as a radiometer scientist or user, it's important to be able to flag these, discard them, but also through the regulatory process, try to work through the process to try and eliminate these sources if possible, or establish regulations that make it possible to avoid these sources of interference. Some of these are illegal, some of these are not illegal. In the L-band spectrum, SMAP and SMOS missions are very active with enforcing the regulations. They're reporting violations to the local spectrum management authorities, who do go out and find these sources and have them turned off. Many of them are, just for example, there are a number of wireless camera systems that have been found that are not supposed to emit in these bands, but the receiver degraded over time or something and started emitting. We can find them, they go turn them off. So it's an ongoing process of continual reporting and trying to get sources managed. So to kind of, about time to wrap up here. So, microwave radiometry is an important application for monitoring Earth's environment, for getting weather forecasts and so on. We think it's an important application to protect as part of spectrum policy. So participating in the spectrum management process, being aware of this type of sensors is important for future spectrum managers so that you understand what the issues are and how to keep the spectrum protected for these. Definitely, there's a lot of research in joint communication and passive user coexistence. I certainly work a lot in that area, but having some protection of protected spectrum is very important so that we have these important sort of gold standard measurements where we're certain that things are working well, and use those to evaluate other candidate measurements. All right, I'll stop there, and thanks for your attention.
Thanks, Joe.
Thank you.
All right.
Thank you.
Any questions? So we kind of got a sense in the morning, well, what questions are coming up. We kind of got a sense in the morning about what it takes to build an Earth-based radio astronomy instrument. So what does it take to build an in-orbit satellite-based Earth-observing instrument, and what does it take to launch one?
Yes. Yeah. Well, a microwave radiometer is basically just a radio receiver, and it's a fairly straightforward radio receiver in that it has typically a fixed, what does a receiver has? It has an antenna, it has a filter, it has a low noise amplifier. We're going to get the data through. We don't necessarily need to discretize it at a high data rate necessarily. So it's but we need to have high precision measurements. So the thing that distinguishes a radiometer receiver from other receivers in that aspect is that you include internal noise sources that you know what their emissions are, to help with calibrating the receiver so that you can make precise measurements. I didn't talk much about calibration here, but as we said, precision is very important. So a radiometer receiver is distinguished by its calibration sources, by its temperature control aspects, but it's not, you can certainly build a radiometer receiver for not that much expense. It takes some careful lab tests to make sure you're getting high precision, but these are not high cost instruments necessarily. For getting into orbit, certainly in the past, we were building large flagship missions that took a long time for development, lots of very high perception of risks, so a lot of review processes and so on to make sure we would have no failures. But nowadays, the new space world makes it such to put instruments on CubeSats. We can have a higher risk tolerance, do things much more rapidly. The microwave radiometer for atmospheric observations is kind of a killer app for CubeSats. So there are a number of radiometers on CubeSats that are making high impact results. And, a CubeSat, you can get into orbit for, tens of thousands of dollars these days. So I would say it's certainly feasible to have a radiometer in orbit for to the tune of less than 100K at the present time. Now, that's accepting some higher degree of risk than we would have accepted in the past, but definitely the new space activities make this a lot more active area, a lot of activity going on these days in this area.
Maria, we have a question in Charlottesville.
Yes, please go ahead.
My question is
Yeah,
what is the Nyquist sampling rate, if there are other rates, and if there are, why Nyquist is used?
So, the Nyquist sampling rate, so our radiometer is going to observe in a certain bandwidth. We're going to have a filter. So our receiver will have a filter on it, an analog filter, say, that's going to set the bandwidth of the information coming into the receiver. So then when I say Nyquist rate, I mean sampling it basically, more or less twice that, a rate twice that bandwidth, the Nyquist rate of any bandwidth. And, yes, it's true that there are different ways of implementing the averaging process. In the end, even though I call that Nyquist sampling, I don't necessarily need to record all of these Nyquist samples. So I may have 100,000 Nyquist samples I can make in a certain integration time, but in the end, all I'm going to do with those Nyquist samples is just average the noise power. So in the end, in radiometry, there is the meaning of Nyquist sampling. It translates into this fact that the precision goes as the square root of the time bandwidth product. It's really the time bandwidth product that's the governing factor here. But thinking about Nyquist sampling helps us to understand how the time bandwidth product maps into the precision of our brightness temperature estimate. So I don't know if that answers your question, but I hope so.
Yeah.
In the end, I'm not going to record all of those Nyquist samples. I'm just going to average the power over all of them and report one number at the end. But by doing so, the precision of the number that I get after that averaging will be basically 1 over the square of the time bandwidth product, which you can translate into a number of effective samples in terms of the Nyquist sampling rate.
All right, great. What other questions do we have?
Oh, I have a
Yes, please go ahead.
okay. I have a question. So, do you use like radiometers to measure gases in the atmosphere? And if so, like what type of gases? And do you think that radiometers will be used to measure in the future?
Yes. So below 100 gigahertz, the only gas we're really measuring below 100 gigahertz is water vapor. So we're, definitely water vapor is a big weather factor, and radiometers provide very valuable information about that. We use the oxygen absorption line. We use the absorption of oxygen in the atmosphere to measure the temperature profile. But we don't try to measure how much oxygen there is, because it turns out oxygen is pretty well mixed. There's not a whole lot of information about how much oxygen there is. If you go above 100 gigahertz, there are other trace gases that you become sensitive to. And so we sort of start crossing into the terahertz realm there. And there is a lot of interest in using, you can find microwave radiometers operating 600 gigahertz, 500 gigahertz that are measuring other gas species in the atmosphere, also measuring ice properties in the atmosphere. So we can also, at those higher frequencies, we might measure some precipitation properties, for example, snow, information about snow rates, and so on. So there are a variety of things you can measure, but below 100 gigahertz, it still remains for the atmosphere, water vapor, temperature profiling, and then a lot of surface applications. I should mention cloud liquid water as well. Also snow rate. So I would say it's precipitation, snow rate, water vapor, temperature profile, those sorts of things for the atmosphere.
Thank you.
I like the second part of this question. What will radiometers be used for in the future, do you think?
Yes, well, certainly we want to continue the applications they're used for at present. The interest in improving our understanding of Earth, improving our weather forecasts, and so on, motivates continued improvements in precision of our measurements. There is a lot of interest from one current activity from NASA is the so-called planetary boundary layer measurement, which implies for radiometry trying to get temperature profile information in much lower regions of the altitude within, say, the range 0 to 2 kilometers. Our temperature profiles I've been talking about so far typically extend from a few kilometers and upwards in the atmosphere, but there's a lot of interest in trying to get even lower in the atmosphere. And there's a field, there's an ongoing activity called hyperspectral radiometry, where we want to make much wider bandwidth atmospheric emission measurements, say from not just from 50 to 52 gigahertz, but from 40 to 80 gigahertz, for example. And by doing so, and do so at much finer spectral resolution. And the goal of that is to try and get much finer resolution in our atmospheric temperature profiles, including information close to the Earth's surface in the planetary boundary layer. Certainly that implies operating outside of protected bands, which would have to be done opportunistically. But there's a lot of current research going on about future sounding instruments using so-called hyperspectral radiometry to get much finer atmospheric temperature profiling. I myself work in wideband measurements at frequencies below a gigahertz. And for there, we're trying to sense the temperatures inside of ice sheets. We're trying to sense more information about sea salinity. That's also done opportunistically. That's a very crowded part of the radio spectrum. So coexistence and spectrum sharing and so on are very important there. Being able to identify other transmitters and filter them out, try to measure thermal noise at the same time you see these other emitters. That's done opportunistically. But there's a lot of interest in that at the current time as well. There's a European mission called CryoRad under development to operate a radiometer from 500 to 400 to 2,000 megahertz in space in the future. So there's a lot of activities going on. Continues to be a very active field of research. Encourage anyone who's interested to get involved and learn more about it. You can learn more through the IEEE Geoscience Remote Sensing Society. Feel free to contact me as well.
All right, great. We have one more question, Albany. Yeah. Okay, so the question is, how do you calibrate the radiometer?
Yes, certainly. Well, again, we're trying to make these very high precision measurements. So any time we want to make a high precision measurement, this is sort of to the tune of 1 part in 10 to the 4, 1 part in 10 to the 5, something like that. Calibration becomes a big issue. And calibration means that, when we're measuring this noise power, we want to know exactly how many watts it is, or in other words, translating that exactly how many kelvins it is. So it's all about making a system that can measure a number of watts very precisely. And whenever you have a system that needs to be calibrated, calibrating means that I'm going to take this system and have it look at something. I know exactly what this source is. Okay, so those are a calibration standard or something. And so microwave radiometers have internal sources of known number of watts of noise power that are built into the radiometer. And we call those calibration loads. And so a radiometer typically, as it operates, will occasionally switch its measurements, not to look at the antenna, but to look at one of these internal sources of information called calibration loads. And we typically have a so-called hot load and a cold load so that we can get a linear function that scales measurements of our power measurements of our radiometer into watts or brightness temperature. So there's an internal calibration process. There's also an external calibration process where we have our radiometer look out at the environment at some source of known noise power as well. And, for radiometer instrument people, calibration is certainly one of the main topics we work on. We try to develop very precise calibrations. And, it's certainly a continued field of research. There's been a lot of impressive progress. We can calibrate radiometers pretty well these days to the sub-Kelvin levels.
So, yeah, that's a great question then. You basically need to keep sanity checking your instrument. And how often do you need to do that?
So if you think about that, we'll want to do this correction, this recalibration of our instrument on timescales over which we think the system is varying.
Mm-hmm.
And it turns out, a radiometer receiver tends to have a lot of gain in there. There's a bunch of amplifiers. So the gain of your receiver can be to the tune of 60 to 100 dB. And if you think about amplifiers, the gain of an amplifier can vary with time, with temperature. And so in a radiometer, the internal calibration can occur on timescales as fast as every 100 milliseconds.
Wow.
And so, yeah, it's because anything that causes our receiver gain to vary, we need to correct for that. So we need to calibrate very frequently.
In spectrum measurement, we should be learning a lot from you guys.
I
All
would
right.
say if we're trying to observe spectrum occupancy,
Yeah,
you may not need to observe that to the level of 10th of a Kelvin,
yeah, for
So-
sure. But still, yeah. Maybe not calibration at the time scale that you do in remote sensing, but certainly some. All right, what more questions do we have? Okay, going once, going twice. If not, we'll break for lunch and we'll let Joel have his lunch as well. And thank you again so much for joining us.
Thank you. Bye.